Vector Calculus, Lecture 13. Actually, the 14th class, but the 12th class was the first midterm exam. And we are doing chapter 15, which is functions of several variables. And now we're getting into the serious stuff, which is the heart of the course. And you might have a function of two variables. So if the variables are x and y, maybe z is f of x, y. This is a function of two variables. Or a function of three variables, x, y, and z. And let's say we let w be f of x, y, z. And so, for example, you might have f of x, y equals x squared plus y squared. Or f of x, y equals 9 minus x squared minus y squared. Or even f of x, y equals the square root of 9 minus x squared minus y squared. So these are examples of functions of two variables. And then you always have to ask for any function, what is called the domain of the function, which means the set of vectors, x, y, if it's a function of two variables, or x, y, z, if it's a function of three variables, for which the function is defined. Now, for the function f of x, y equal x squared plus y squared, the domain is all vectors x, y. Right? Because for any pair of vectors x and y, any pair of numbers x and y, you can compute x squared plus y squared. But for the function square root of 9 minus x squared y squared, the domain is not all x, y, because you're taking a square root. So what you're taking the square root of must be greater than or equal to 0, which is the same as x squared plus y squared less than or equal to 9, which is the set of points on or inside the circle of radius 3. So for this function, the domain is the set of all pairs x, y, all vectors x, y, such that x squared plus y squared is less than or equal to 9. That's the domain of the function. If you have the function f of x, y, z equal x plus y over z, what is the domain of this function? Well, the domain is anything where makes sense, where it means z is non-zero. So this is the domain is the set of all x, y, and z, where z is not 0. So if you looked at this in space, if z equals 0, that's the xy plane in space. So the domain is everything either above the xy plane or below it. You can't have z equals 0. And there are a number of examples in the text and exercises where you have to look at a function and figure out what the domain is. And usually there are only two conditions that keep a vector from not being in the domain. So to find the domain of a function, recall that the square root of something, I don't know what I should call it, square root of p only makes sense when p is greater than or equal to 0, and let me call this q, it's not like that. And that when you have p over q, you must have the denominator not equal to 0. So you can't take the square root of a negative number and you can't divide by 0. And looking for square roots and quotients in the definition of a function will usually give you all the constraints that there are on the domain. Right? For a function of two variables, z equal f of x, y, the graph of the function is a surface in three-dimensional space. So if you think of your three-dimensional space as being like this is x, y, this is z. For any point xy, f of xy is some number, so you look at the point x, y, and the z coordinate is f of xy. And over whatever is the domain of the function, thus will sketch out some surface in three-dimensional space. So the graph of a two-dimensional function is a surface. And they're hard to draw. Maple plots three-dimensional surfaces well. So if you know Maple or get Maple and can figure out how to use it, just for fun, you can use Maple to graph functions of two variables. You can get some very beautiful, complicated, interesting surfaces in space using Maple. Simple examples you can try to do by hand. So here's what is called a paraboloid. We have z is some function of x and y, and the function is just x squared plus y squared. So at the point 0, 0, z is equal to 0. On the circle, x squared plus y squared equals 1 in the xy plane, the value of the function is 2. So the height is 2. If you look at the circle, x squared plus y squared equals 4, that's a circle of radius 4. The height of the function is 4. In fact, if you let x equal 0, so you're just looking at, on the y-axis, f of 0y is y squared. So z is y squared. So it's just this parabola. I can't draw it very well. And the graph of this function is this parabola rotated around the z-axis. So this rotated parabola is what's called a paraboloid. What usually gives you a decent idea of what the shape of the surface might look like is to draw the level curves of a function. Level curves of a function of two variables, f of x, y. And the level curve is for some number c to find all the points where f of x, y is equal to c. So or maybe I should call it Z1, Z2, some fixed number Z. So let's look at this example again of a paraboloid f of xy equal x squared plus y squared. So we have the level curve, all points where f of xy equals 0. That means x squared plus y squared equals 0. That's the same as xy is 0, 0. So in the xy plane, just the origin is the level curve at 0. What about the level curve f of xy equal 1? That's all points where x squared plus y squared equals 1. That's the circle. Of radius 1. So 1. That's the level curve, f of xy equal 1. What's the level curve? F of xy equals 2. Those are the points x squared plus y squared equals 2. This is also a circle of radius square root of 2. So square root of 2 is about 1.4. So that's a circle that looks something like this. That's the level curve of radius 2. Circle of radius 1. What's the level curve? F of xy equals 3. That's x squared plus y squared equals 3. That's a circle of radius square root of 3, which is about 1.7. And f of xy equal 4, x squared plus y equals 4. That's a circle of radius 2. And so on. So these are the level curves of the function. And the closer these curves are to each other for equally spaced values of the right-hand side, the faster this curve is moving, the surface is moving up, and the further apart these curves are, the more slowly the function is increasing. So the best thing to do is study the pictures in the book. So study the figures in text to understand level curves. That's really the suggestion, because it's hard to draw these things by hand, and you get an idea of what's going on by looking at these level curves. No. Okay. So let's just recall something about calculus 1, calculus 2. If you have a function of y equal f of x, function of one variable, the graph is a curve. This is the graph of y equals f of x. And at any point on the curve, if you want to approximate it by a tangent line, you have a tangent line at the point y naught equals f of x naught. And this is the line through, this is the point x naught, y naught on the curve. This is the line through x naught, y naught with slope equal to the derivative of the function at x naught. Let me just write it as derivative with respect to x at x naught. Right? And you spent most of the first semester of calculus studying derivatives of functions and these tangent lines to curves. The derivative df dx in some sense measures the rate of change of the function at a point, say x equal a. Right? We define the derivative of f at a. You take f of a plus h minus f of a divided by h, and take the limit of that as h goes to 0. Right? It's like here you have a, here you have a plus h. This height is f of a. The height of this is f of a plus h. So this difference is how much the function changes as you go from a to a plus h. And to get something like the rate of change, you take this divided by h. So as you change the x coordinate by h, the y coordinate changes by f of a plus h minus f of a. So this is something like the rate of change of the function at h. And you take the limit as h goes to 0, and that's the derivative. So this is Calc 1. So by the time you get to Calc 3, there are two possibilities. One is you've forgotten this completely, in which case you'll be in a lot of trouble. And the other is you haven't forgotten it, and you'll be able to understand pretty easily what partial derivatives are. So we want to be able to extend this notion of the rate of change of a function of one variable to the rate of change of a function of two variables. And we also want to extend the idea of the tangent line to a curve to, let's see, what would be the analogous thing? It would be you have a surface, and on this surface, you approximate the surface near a point by a plane. So instead of a tangent line on a surface, we'll have a tangent plane. So we want to be able to extend the notion of derivative and tangent line for a function of one variable to derivatives and tangent planes for functions of 2 or 3 variables. The issue is, of course, if you want to know what is the rate of change of the function on a surface, so suppose you have some function z equals f of x, y, and this is the point, let's say x is a, y is b, and z would be f of a, b. So you want to know at this point how fast the curve is changing, this function is changing. And the problem is the rate of change can depend on what direction you're looking in. Because you can have curves which look like saddle points, and it's completely above me to be able to draw a saddle. So I can't draw a saddle, but at a saddle point, in one direction, the curve looks like this through this point, and another direction, curve looks like that through the point. So in one direction, the function is decreasing, but in a different direction, it's increasing. So what really is important, if you want to extend the notion of derivative from a function of one variable to a function of another variable, you have to look at what we call the directional derivative. It's the rate of change of a function. So here you are in the xy plane, and here's your point AB. you can take a line in this direction, or in this direction, or this direction, or in this direction, and you can restrict the function to just this direction or just this line, and ask her what is the rate of change of the function as you just move along, just go in that direction. And the two basic cases are the directions are x direction and y direction. So from a point, you're going to ask, how does the function change as you go from a, b, and you only change x? So from a to a plus a, b to a plus h comma b. Or you can look for the rate of change in the y direction. You keep a fixed, and you go from a, b to a, b plus h. So this is the x direction. This is the y direction. And the directional derivatives in those directions are called the partial derivatives with respect to x and y, respectively. So the partial derivative of, let's say we're looking at a function of two variables, z of x, y, at the point a, b, in the x direction is the following. Here you have the point a, b, and you just keep b fixed and you change the x coordinate, a plus h comma b. This can be, the h can be positive or negative, can be to either side. And we look at the difference, f of a plus h comma b minus f of a b. That's the difference between the value of the function here and the value of the function there, and divide it by h, and take the limit as h goes to 0. And this is the partial derivative of f with respect to x at ab. And again, just as with derivatives, there's several bits of notation. You can write f sub x of ab, or partial of f with respect to x at ab. And there are even other notations, but these are the two basic ones. So that's the partial derivative in the x direction. The partial derivative of z equal f of xy at ab in the y direction. So we have the point AB, we keep A fixed and we change H. So we go from A comma B to A comma B plus H. And we look at how much the function changes as the B coordinate changes by H. So it's f of A comma B plus H minus f of AB divided by H. That is, if you go H units, what is the amount of change relative to H? Take the limit of that as H goes to 0. And this is the partial derivative of f with respect to y at AB, or partial of f with respect to y at AB. In one variable, you use dx for derivative. And in several variables, instead of d, we use kind of a curly d. Right? So this is change of notation. This is one variable. This is 2 or 3 variables. So instead of d, you use this curly d for notation. And this tells you the rate of change of the function in different directions. So let's look at a couple of examples, and we'll compute them, and then we'll see very quickly how everything reduces just to calc 1. So suppose I take the function f of x, y equals x squared y. And I want to compute the partial derivative of f with respect to x at some point x, y, or f sub x at x, y. So we keep y fixed and change x. So we have f of x plus h comma y minus f of xy divided by h. We want to take the limit of that as h goes to 0. So we do this just the way we did in Calc 1. What is f of x plus h comma y? F is x squared y, so f of x plus h comma y is x plus h squared y, which is x squared plus 2 hx plus h squared times y, or x squared y plus 2hxy plus h squared y. So f of x plus h comma y is this x squared y plus 2hxy plus h squared y. Sorry, f of x plus hy minus f of xy minus f of xy, which is x squared y. And we see that this term and this term cancel, plus this minus this. So we're left with just these two terms. This equals 2hxy plus h squared y. So f of x plus h comma y minus f of xy is equal to this. I can actually factor an h out of this. This is h times 2xy plus hy. And then I divide by h, and the h's cancel. This is 2xy plus hy. So the partial of f with respect to x and xy is the limit as h goes to 0 of this expression, 2xy plus hy. This doesn't depend on h at all. That doesn't change. But as h goes to 0 and y is fixed, hy goes to 0. So 2xy is the answer. So the partial of x squared y with respect to x is 2xy. This is exactly the same as saying, and it's also correct to say, like you treat y as a constant, so this is then the derivative of x squared is 2x, so you get 2x times y. And in the same way, if you take the partial with respect to y of xy of the function x squared y, if you treat x squared as a constant, x is fixed, it's just the partial of y with respect to y, which is 1. So the partial derivative of f with respect to y is x squared. Any questions about this? Let's just look at a couple more examples. Suppose we have f of xy is the function sine of the product xy. Partial of f with respect to x, if you treat y as a constant, the sine of x times a constant is, when you differentiate with respect to x, sine of xy, you get the cosine of xy times the derivative of xy with respect to x, which is y, because x is like a constant. And the partial of f with respect to y, you differentiate this with respect to y, you get the cosine of xy times the derivative of xy with respect to y, which is x. Right? Suppose we have the function g of xy equals x squared e to the xy. So the partial of g with respect to x, by the product rule, the derivative of x squared e to the xy is the derivative of x squared, which is 2x times e to the xy, plus x squared times the derivative of e to the xy with respect to x. So that's e to the xy times the derivative of xy with respect to x, which is y. And if I differentiate this with respect to y, x squared is like a constant. The derivative of e to the xy with respect to y is e to the xy times x. So we get x cubed e to the xy. So just as for your pleasure, if you like, suppose I have the function xy equals the log of x cubed, log of the thing, x to the fourth y squared. What is the partial of h with respect to x? And what is the partial of h with respect to y? I'll give you a couple of seconds to try to figure that out. Remember, the derivative of log x is 1 over x. And let's see. Anyone have an answer? So the derivative of log x is 1 over x. So the derivative of the log of x to the fourth y squared is going to be 1 over x to the fourth y squared times the partial derivative of x to the fourth y squared with respect to x. Derivative of x to the fourth is 4x cubed times y squared, which is like a constant. That's the partial of this with respect to x. And if you differentiate this with respect to y, you get 1 over x to the fourth y squared. And the derivative of this with respect to y is x to the fourth. Derivative of y squared with respect to y is 2y. So that's what we get. And of course, just as with functions of one variable, if you take a function of one variable and you differentiate it, you can differentiate it again. So let's look at an example. F of x, y equal, simplest examples are always polynomials. If I take the partial of f with respect to x, I get 3 times derivative of x to the fourth is 4x cubed, so that's 12x cubed y. Differentiate with respect to x, minus 2xy is minus 2y. Differentiate with respect to x. Here we get plus 5y cubed. But this is another function of f and y, of x and y. So I could differentiate this, for example, with respect to x. So what is called the second partial derivative of f with respect to x, which means the derivative with respect to x of the derivative with respect to x. So I have to differentiate this with respect to x. Derivative of x cubed is 3x squared. So I get 12 times 3, which is 36x squared y. And each of these is a constant with respect to x. So the derivative with respect to x is these is 0. So the second partial derivative of f with respect to x is 36xy squared. If I take the partial with respect to f, of f with respect to x, and then the partial of that with respect to y, which I can write as the second partial of f with respect to y with respect to x. What is this? So if I differentiate this with respect to y, this is the derivative with respect to x. If I then differentiate this with respect to y, I get 12x cubed minus 2 plus 15y squared. Right? So this is the second partial of f with respect to x. This is the second partial of f with respect, first with respect to x and then with respect to y. Suppose I take the partial of f with respect to y for this function. When I differentiate this with respect to y, I get 3x to the fourth minus 2x plus 5x. The derivative of y cubed is 3y squared, and 3 times 5 is 15, so I get 15xy squared. And then I can, again, with the partial with respect of f with respect to y, I can differentiate the partial of f with respect to y, again with respect to y. So that's the second partial derivative of f with respect to y. Or I could take the partial of f with respect to y and differentiate that with respect to x. So that's the second partial derivative of f with respect to x and y, but in this order, first y, then x. So here I differentiate f with respect to y, and I get this. And when I differentiate this again with respect to y, this is 0, and derivative of y squared is 2y, so I get 30xy. Here I differentiate with respect to y. If I then differentiate with respect to x, I get 4x cubed times 3. I get 12x cubed. Differentiating with respect to x, I get minus 2 plus 15 y squared. So those are the 4 second partial derivatives. And I notice actually this equals this. So these two are the same. So in this example, at least, if I take the partial of f with respect to x and differentiate that with respect to y, I get exactly the same thing as if I do my derivatives in the opposite order. Partial of f with respect to y, and then the partial derivative of that with respect to x. And for nice functions, for continuous functions, this is always the case. So for nice, smooth, continuous second derivatives, it always will be the case that the second partial of f with respect to x and y is the same as the second partial of f with respect to y and x. So this will certainly happen if f has continuous second derivatives. That's actually a theorem that takes a lot of work to prove in advanced calculus, but we're not in advanced calculus here. This is really still beginning calculus for functions of several variables. Now, what's very interesting, and what is really the most important rule for differentiating functions of one variable in Calc 1 is the chain rule. So in Calculus 1, if you had y is f of g of x. So suppose you had a function, let's see, I'm not sure what are good letters in this. So you have a function w equals g of x, and f, and say y is some function of w. So you have the composite function y equals f of w, but w is g of x. which we usually write as f composed with g of x. So this is really just a review. Calc 1. dy dx, the derivative is f prime of g of x, g prime of x, which you could also write as dy dw times dw dx. If w is g of x, g prime of x is dw dx. If y is f of w, dy dw is f prime of w, or f prime of g of x. So for example, if you have y is the sine of x squared, dy dx. So this is like you have the function y is some function of w, sine of w. W is some function of x, which in this case is x squared. So dy dx is dy dw dw dx. If y is sine w, dy dw is cosine w. dw dx is 2x, or 2x times the cosine of w, which is x squared. Right? So you have to know, because we're not, and you have to just review it if you don't remember it, that if you have y is sine of x squared, the derivative is 2x cosine of x squared. And if you need some review practice with this, then I encourage you to go to the Math and Statistics Help Center in Gillette Hall, where there are people who will go over all of this with you very carefully. Okay. So this is the chain rule for functions of one variable. Now you can have a function of two variables, which is a composite function, in several different ways. And here is the first of those several ways. Suppose you have a function x of t and y of t, and you have a function z, which is a function of x and y, but x and y are both functions of t.
From ourtalkdio.com. Tea is often associated with relaxation or sleep, but it can also be used as an energy booster to get you pumped up for your workout.
That's the Alexa. So Z is actually a function of t. Let me just give an example. So this makes some sense. Suppose you have the function z. I'll just pick the first example in the text, which is always a good example. Say, suppose z is a function of x and y, x squared minus 3y squared plus 20. So this is some function of x and y. But x is actually a function of t. And y is a function of t. So z is really a function of t. Z is equal to x squared, 2 cosine t squared, minus 3y squared, minus 3 2 sine t squared, plus 20. Which, if you wanted to write it out, would be 4 cosine squared t minus 12 sine squared t plus 20. So you could just write dz dt and just differentiate this with respect to t. And if you do that, let me just do it for the record. This is 4. The derivative of cosine squared t is minus 2 sine t. Sorry, it's derivative, let me do this correctly. dz dt is 4. The derivative of cosine squared t is 2 cosine t times the derivative of the cosine, which is minus the sine of t, minus 12 times the derivative of sine squared t, which is 2 sine t, times the derivative of sine t, which is cosine t, and the derivative of 20 is 0. So this is minus 8 sine t cosine t, minus 24 sine t cosine t. So I get minus 32 sine t cosine t. So for the record, let's just remember this, or if you want to write 32 as 16 times 2, 2 sine t cosine t is the sine of 2t. So you can also write it like this. But there's another way. So this is explicitly putting in the values of x as a function of t and y as a function of t. But we also have a chain rule. And let me just write down what the chain rule is in this example, in this case, for a function of 2 variables. If you have z is some function of x of t and y of t, or if z is some function of xy, and x is a function of t and y is a function of t. So the composite function is a function of t. So it's a function of one variable, dz dt. But the chain rule says this is the partial of z with respect to x, dx dt, plus the partial of z with respect to y, dy dt. So in more advanced calculus, one proves this, but it has to be much more advanced calculus. And that is the chain rule. Well, chain rule 1, because it's the first example of a chain rule. So let's see what this formula tells us in the example that we just had. In the example we just had, we had z was x squared minus 3y squared plus 20. X is 2 cosine t, and y is 2 sine t. So this is z. The partial of z with respect to x is 2x. And the partial of z with respect to y is minus 6y. And dx dt is minus 2 sine t, and dy dt is 2 cosine t. So if I take these 4 quantities, 1, 2, 3, 4, and I plug them into this formula, what do I get? I get dz dt is dz dx, 2x, dx dt minus 2 sine t, plus dz dy minus 6y, dy dt, which is 2 cosine t. X is 2 cosine t. So I have minus 2 times, I have 2 times minus 2, minus 4. So let me just write, this is minus 4x, which is 2 cosine t sine t, minus 6 times 2 is 12 cosine t times y, which is 2 sine t. So this is minus 8 minus 24 is minus 32 sine t cosine t, which minus 32 sine t cosine t, exactly what we had before. So this is an example of the use of the chain rule. And yeah. Let me do another example. Again, this is the rule one has to remember, where z is a function of x and y are both functions of t. So suppose z is square root of r squared plus s squared. Doesn't matter what letters we use. Where r is cosine. Oh, well, that makes you stick with x and y just so it's easier. So x is cosine of 2t, and y is the sine of 2t. X is square root of x squared plus y squared. So z is x squared plus y squared to the 1/2. Partial of z with respect to x is 1/2 x squared plus y squared to the minus 1/2 times 2x. The 2 and the 1/2 cancel. We get x over the square root of x squared plus y squared. Partial of z with respect to y is 1/2 x squared plus y squared to the minus 1/2 times 2y, which is y over the square root of x squared plus y squared. And dx dt and dy dt are just Calc 1 problems. So dz dt is the partial of z with respect to x over the square root of x squared plus y squared, times the partial of x with respect to t, which is minus 2 sine dt, plus the partial of z with respect to y, which is y over the square root of x squared plus y squared, times the partial of y with respect to t, which is 2 cosine 2t. Now, x squared plus y squared actually, let's put this in. So x is cosine 2t. So this is 1 over the square root of x squared plus y squared. Let me just factor that out. I have minus 2 sine 2t cosine 2t plus y times this, 2 times sine 2t cosine 2t. And minus 2 plus 2 is 0. So this is 0. So dz dt is identically 0, always. And if you want to know why that is, if x is cosine 2t and y is sine 2t, x squared plus y squared is cosine squared plus sine squared, that's 1. So z is just a constant function 1, and the derivative of a constant is 0. So this is nicely consistent. So there are really two forms of the chain rule, and this is the first. In this form of the chain rule, you have z is some function of x and y, and x is a function of t and y is a function of t. So z really is some function of t, and you want to find dz dt. But we can also have the case where z, so this is case 1. In case 2, z is some function of x and y, but now x and y are both functions of, let's say, two variables. So x is a function of variables s and t, and y is a function of s and t. So z becomes a function of these two variables s and t, and we want to find what is the partial of z with respect to s, and what is the partial of z with respect to t. And the chain rule says the following: the partial of z with respect to s is the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y times the partial of y with respect to s. And when you differentiate z with respect to t, the partial derivative of z with respect to t is the partial of z with respect to x, partial x with respect to t, plus partial z, partial y, partial t. So this is the second case of the chain rule, where z is a function of two variables x and y are each functions of two variables s and t. So let me just, so again, the proofs are difficult at this stage in your math education, but if you get to advanced or more advanced calculus, then you prove these, but the proofs take a certain amount of work, and it's not what we do here. So let's look at an example. Suppose z is sine 2x cosine of 3y. So z is a function of x and y. But x, in turn, is a function of s and t, and y is a function of s and t. X is s plus t, y is s minus t. So let's compute the partial of z with respect to s. So we take the partial of z with respect to x. Partial of z, so if z is sine 2x cosine 3y, so the partial of z with respect to x, cosine, sine of 2x, when you differentiate with respect to x, you get 2 cosine 2x times cosine of 3y, which is a constant. That's the partial of z with respect to x. The partial of z with respect to y, sine 2x is a constant. The derivative of cosine 3y is minus 3 sine of 3y. So that's what these partial derivatives are. So the partial of z with respect to s is the partial of z with respect to x, 2 cosine 2x cosine 3y times the partial of x with respect to s, which is 1, right? Plus the partial of z with respect to y, that's minus 3 sine 2x sine 3y times the partial of y with respect to s, which is 1. So that's the answer, but then you put in what, if you like, you put in what s and t are, you get 2 times the cosine of 2s plus t, cosine of 3s minus t, minus 3 times the sine of 2s plus t, sine of 3 times s minus t. That's the partial of z with respect to s. And to learn the chain rule, Practice, practice, practice. That is, the only way to learn this is to do a lot of exercises. And I try to give odd numbered problems in the exercises because the answers are in the back of the book and you should change them. By the way, practice is spelled with a C, so let me do that correctly. And I'll do more examples on Wednesday. So I started out by saying with a function of several variables, the graph is some surface in space and if you take a point A, B in the plane, in the graph of the function in the surface, you have the point A, B, f of A, B. And we took the partial derivatives in the x direction and in the y direction. In the x direction, you had some curve in the surface, and in the y direction, you had another curve in the surface. And the rate of change along those curves are the partial derivatives. But we want to know in general, if you go off in any direction, how rapidly or slowly is the function changing in that direction? So we want to figure out a way to intelligently define the directional derivative of z equal f of x, y at the point AB in the xy plane in the direction u, some vector u, which is not the zero vector. So there really is, there's some direction. So this is in some direction u. So if you're looking at the xy plane, you would have the point AB and you have a certain direction u. So you want to look at, see, from the point AB to the point with coordinates a plus u1, b plus u2, so along this line, from here to here, in the surface, you have f of a plus u1, b plus u2, minus f of b. That's the change in the value of the function as you move along this in this direction from the point AB to AB plus u. U is the vector u1, u2. And let's say this distance is h from here to here. And if you decompose that into its components, you have h1 and h2. It's a change in a of h1, sorry. That's not the way I want to say it. I want to say that this is, well, this is really going to be h times u2 And this horizontal distance is HU1. HU. So we take, so let me just say this again more carefully. So we have a direction. I want to take a unit vector, U, with coordinates U1, U2. That's my vector U. And I take a point in the plane AB, and then I go to the point which is AB plus H times this unit vector. So this distance is H, because the length of HU is H times the length of U, which is 1. And U is U1, U2. So this is coordinates HA plus HU1, B plus HU2. So at this point, the value of the function is f of A plus HU1, B plus HU2. I subtract the value of the function at AB, and the distance between them is the length of the vector HU, but U is a unit vector, so that length is 1. And then I take the limit as H goes to 0. So this is the slope of the secant line. So here on our surface, here is f of AB, and here is f of A plus HU1, B plus HU2. And this change from here to here is this difference, divided by the length of this line segment H. So if we have U, U1, U2, a unit vector, in the XY plane, the directional derivative of f at the point AB in the direction of this unit vector U is f of A plus HU1, B plus HU2 minus f of B, divided between the distance between these 2 points in the plane, which is H. Take the limit as H goes to 0, and we write this as capital D sub U of f at AB. So that's the formal definition, but there's a theorem which allows us to calculate the directional derivative much more easily. So the directional derivative of f at the point AB in the direction U is given by this formula, but we can also write this as the following. If I take the partial derivative of f at x and the partial derivative of f with respect to y at AB, look at that vector, dot product with the vector U1, U2, that's the directional derivative in the direction U. So this is equal to, if I take the dot product, U1 partial of f with respect to x at AB plus u2 partial of f with respect to y at AB. And this reduces the calculation of a directional derivative to the calculation just of the partial derivatives. So let's look at some examples of this. Let me just give one or two examples. And we're covering a lot today, but from now on and through the rest of the course, we cover a lot every day. It's a very rich syllabus. So everything I did today, I want you to study, but I'm going to review it again with more examples on Wednesday. So here's let's look at one first example. Suppose z is a function of x and y, and it's just the function 1/4 x squared plus 2y squared. Plus 2. And we take P naught to be the 0.32, and we consider the unit vector u equal 1 over root 2, 1 over root 2. So this means that in the plane, here's the point P naught, 3, 2, 1 over root 2, a unit vector on the line y equal x, that's what u is. This is a vector of length 1. And so I want to find the directional derivative of my function at the point P naught of 3, 2 in the direction along this line y equals x. So in this direction, what is the directional derivative? So for this function, the partial of f with respect to x is 1/4 times 2x, which is x over 2. So at the point 3, 2, the partial derivative is 3/2. For this function, the partial of f with respect to y is 1/4. The derivative of 2y squared is 2 times the derivative of y squared, which is 2y. It's just y. So the partial of f with respect to y at the point 3, 2 is equal to 2. So the directional derivative of the function f in the direction u at the point 3, 2 is 1 over root 2 times 3/2 plus 1 over root 2 times 2, which is 7 over 2 root 2. If we took a different direction, the direction v equal to 1/2 minus root 3 over 2. So that vector is a unit vector in this direction. This angle is minus pi over 3. This is a unit vector in this direction. In the direction of v, for the function f at the point 3, 2, it's 1/2 times 3/2 minus root 3 over 2 times 2. So that's equal to 3/4 minus root 3 at the directional derivative. Okay. All right, so now we're entering an entirely new domain. We're looking at functions of 2 or 3 variables. Today, mostly I looked at, entirely, I think, I looked at functions of 2 variables, and functions of 3 variables have exactly analogous chain rules and rules for computing directional derivatives and partial derivatives. And this is really what we're going to spend the rest of the semester studying. So I encourage you to spend as much time as you can studying the text and looking at the pictures in the text, because they're very important, and doing the homework problems and as many other problems as you can. Always check the answers in the back of the book. And if you can't figure out the answers, I have office hours this week, Tuesday, Wednesday, Thursday at 7, Friday afternoon at 4:30, and I strongly, strongly, strongly encourage you to log on to an office hour and ask questions if you have them. Okay, that's a lot for today. Any questions before we stop?